Good morning, everyone. Myself Tejasri, working as guest lecturer in physics. Today, I am going to discuss about the topic Kronecker delta function and Dirac delta function. So first, coming to its introduction, Kronecker delta function, next Dirac delta function and their certain properties. So in our previous class, we already discussed about this Kronecker delta function and its certain properties. Now in today's session, let us discuss about this Dirac delta function and its certain properties. So coming to the introduction, two distinct but similar mathematical entities exist, both of which are sometimes referred to as the delta function. You should be aware of what both of them do and how they refer. One is called the Dirac delta function and the other Kronecker delta function. In practice, both the Dirac and Kronecker delta functions are used to select the value of function of interest f of x at some specific location in the respective function's domain, that is, to evaluate f of x at some point x equal to x naught. This happens by placing next to the appropriate delta function inside of an integral Dirac and within the summation Kronecker. So as in previous class, since we already discussed about this Dirac delta, this introduction to this delta functions, so we have two mathematical entities which is referring as delta functions. One is Kronecker delta function and the other is Dirac delta function. So we select or choose this particular delta function based on this selection of that particular function, means function. So let us select this, consider this function as f of x. So that respective function domain, which means at some point, since we are going function, so that we evaluate f of x at some point x equal to x naught. So this first equation is of the form Dirac delta function, which is represented in the form of an integral function, and the second equation is the Kronecker delta function within the summation form. So about this Kronecker delta function, we already discussed about in our previous class and its certain properties. Now coming to this Dirac delta function, this Dirac delta function is a generalized function or distribution introduced by Paul Dirac. It is used to model the density of an idealized point mass or point charge as a function equal to 0 everywhere except for 0 and whose integral is equal to 1, which means this delta function can be typically represented as delta of x is equal to infinity at x equal to 0, 0 otherwise, which means this delta function becomes 0 at except 0, which means other this at x equal to 0 it is infinity, other than 0 this delta function becomes 0, which means suppose let us consider a graph. So let us consider this as delta function delta of x. So this point is 1, this is minus 1, this is minus, which means 1, 1, 2, this is minus 1, this is minus 2. Now this is 0, this is 1, this is 2, this is 3. I hope everyone is understanding this graph. So this is the delta function, this is one of the waveform. If we observe this graph here, so let us see the condition is x equal to 0 infinity condition, which means it's x equal to 0 condition. This delta function is going to infinity condition. This delta x is infinity. Otherwise 0, which means at 1 it is below 0, the value at minus 1. At minus 2 it is below 0. So this graph is below 0. So this is the condition, the delta of x, which means this delta x function is at infinity condition, at x equal to 0, and other than 0 they were below the 0. So the value of x at which the delta function becomes infinity, which means this x, the value of this delta function becomes infinite under this infinity condition, can be controlled by substituting x minus x naught. Suppose this delta function is becoming infinite at certain point we are considering as x, then we can control that infinity condition by substituting this x as x minus x naught. So that equation form can be represented as delta of x minus x naught equal to infinity at x equal to x naught, 0 otherwise. One useful way to think of the Dirac delta function is that of the limit of a normalized Gaussian as the width goes to 0. That is, one of the way this delta function, which means we can, this width goes to 0, which means since when this wave function get compressible, which means this wave function compressible, then it becomes, which means then it becomes a very thin form, which means here becomes the wave compressibility, which means the width decreases and its height increases, which means this waveform of its width is decreasing and its height is increasing. In this way, the limit of the normalized Gaussian as the width goes to 0. So when its width becomes 0, then the Dirac delta function can be represented in the form of limit, in the form of the limit condition, which can be represented as delta of x is equal to limit sigma tends to 0 1 by sigma to the root 2 pi e power minus x square by 2 sigma square. So therefore imagine taking a Gaussian and squeezing it into down widthwise, because it is normalized, which means the total area under the curve integrates to numerical value 1. As it is squeezed in the width, the height has to increase. If you make it infinitely thin, then it has to be infinitely tall to compensate, but the total area is always 1, which means by considering this figure, so when we observe this figure here, if this curve crosses this value, then its value is 1. So under below this, its value is 0, which means the point is at minus 5 and plus 5, it is 0. Here near to the 0 value, it reaches to the value 1. So when its width totally, which means completely compressed, this value reaches to its infinite condition, which means width decreases, height increases. Here width decreases, height. So height decreases of its width. So here what we are saying is we are considering a Gaussian surface and squeezing it down widthwise, means we are squeezing, which means we are making its width decreases because it is normalized. The total area under the curve integrates to numerical value 1, which means due to its width decreasing, its integration of that particular curve is value is equal to 1 according to the Dirac delta function. So as it is squeezed in the width, the height has to increase. Since the width is decreasing, it is increasing its height. If you make it infinitely thin, which means under infinite condition, if you are making very thin, then it has to be infinitely tall to compensate, but the total area is always 1. So if the width of it is little squeezed or infinitely it becomes thin, whatever the condition, it is always, which means always the total area is always equal to 1. So before getting into the physical interpretations of what a Dirac delta function might represent, let's consider some more mathematical properties of this function. So according to this Dirac delta function, we have certain mathematical properties. So the Dirac delta function usually appears in an integral form, perhaps most useful. So one of the most important property of the Dirac delta function is integral minus infinity to plus infinity f of x delta of x minus x naught into dx is equal to f of x naught. So this property is one of the most important property. So we can understand this by considering, which means, since we know that integral minus infinity to plus infinity delta of x into dx equal to 1. So this is the condition, which means its integral of its delta function, which means area is always equal to 1. Since we already said total area is always 1, so therefore its total area is always 1. So this delta function. So next, suppose we are applying certain function to the Dirac delta function. So we can represent it as integral minus infinity to plus infinity f of x delta of x minus x naught into dx. So therefore at infinity condition we are writing x minus x naught, x is equal to x minus x naught. So now this delta function is 0, which means this delta function, in order to become this delta function 0, unless its arguments, here its argument if it is 0, then only this delta function becomes 0. Here the argument is x minus x naught. So under this condition, its argument is x minus x naught. So this should be equal to 0. Then only the delta of function becomes 0. So therefore, which means this x minus x naught equal to 0, which means x equal to x naught. The value of x is x naught. Therefore, finally this function will be equal to f of x naught, which means we can say in other form as this function is always depends on this Dirac delta function delta of x. So the function which we applied here, the f of x function, is always depends on this delta function, and this delta function, in order to become this delta function, its arguments should be equal to 0, and its argument should be equal to 0, which means it becomes x equal to x naught. Therefore now this function becomes f of x naught. So this is one of the property of the Dirac delta function. So it has two properties. So one is we already discussed in detail, that is integral minus infinity to plus infinity f of x delta of x minus x naught dx is equal to f of x naught. Is another one is delta of ax is equal to 1 by mod a into delta x. This is the another property. These were certain properties of this Dirac delta function. I hope everyone understood the concept. Thank you.